Okay. A function g is the inverse function of the function f when f of g of x is equal to x for each x in the domain of g, and g of f of x is equal to x for each x in the domain of f. And the function g is denoted by f to this little -1, which is read as f inverse. And you get an inverse function when you interchange the first and second coordinates of each ordered pair. So in this picture, this is the original domain, and domain of f is equal to the range of the f inverse, and the domain of the f inverse is equal to the range of f. Okay. So another way to think of f inverse is undoing what's been done by f. So it's like subtraction to addition and division to multiplication. So you have f inverse to f. And then a property of inverse functions is the reflective property of inverse functions, which states that the graph of f contains the point A, B if and only if the graph of f inverse contains the point B, A, which is, again, you're switching the x and y values, and that's also how you obtain inverse functions. So let's try this problem. Find the inverse function of the square root of 2x minus 3 and verify. So in order to obtain the inverse, we have to change x and y because you're switching the domains and ranges. So the square root of 2y minus 3 is equal to x. And then square both sides. 2y minus 3 is equal to x squared. Add 3 to both sides. 2y is equal to x squared plus 3. And then divide by 2. So you get y is equal to x squared plus 3 over 2. And then when I say y, this should be the f inverse. So in order to verify this, you would just do f inverse of f of x, and that should equal x. And then the f of f inverse of x should also equal x. So, okay, so you get, you would plug in all of this for x for inverse. So, f inverse of f of x is equal to the square root of 2x minus 3 squared plus 3 over 2. That's equal to 2x minus 3 plus 3 over 2. That cancels out, this cancels out, so you are left with x. So that is correct. Now let's do the f of f inverse. So the f of f inverse of x is equal to, now you're plugging this whole thing into x here. So you get the square root of 2 times x squared plus 3 over 2 minus 3. This cancels out, so you get x squared plus 3 minus 3, all under a square root. This goes to 0, so you get the square root of x squared, and that is just equal to x. And you don't need to put absolute values or anything because the domain of this function should be equal to the range of the inverse function. Okay. Next. So then you have to check if the inverse function exists. And you can use the horizontal line test for an inverse function, and this test states that a function f has an inverse function if and only if every horizontal line intersects the graph at f at most once. So if you look at this picture, since the horizontal line test does not pass because when you draw a horizontal line on the graph, it intersects the graph at 2 points, which is more than just once. So therefore, the test fails, and there is no inverse function for this particular graph. Also, if a function is strictly monotonic, which means it's either increasing on its entire domain or decreasing on its entire domain, it's one-to-one, which is one of the prerequisites for being an inverse. So, theorem 5.7, the existence of an inverse function. A function has an inverse function if and only if it is one-to-one. If f is strictly monotonic on its entire domain, then it is one-to-one and therefore has an inverse function. And then there's some guidelines for finding an inverse function. Use this theorem that we just talked about to determine whether the function y equals f of x has an inverse function. If it does, then solve for x as a function of y. So x is equal to the g of y, which is equal to f inverse y. Interchange x and y, and the resulting equation is y is equal to f inverse of x. Define the domain of f inverse as the range of f. Verify that f of f inverse of x is equal to x, and f inverse of f of x is equal to x. And these are the steps that we followed in the previous practice problem too. Okay, so now to take the derivative of an inverse function. So here's another theorem. Continuity and differentiability of inverse functions. So let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. If f is continuous on its domain, then f inverse is continuous on its domain. If f is increasing on its domain, then f inverse is increasing on its domain. If f is decreasing on its domain, then f inverse is decreasing on its domain. If f is differentiable on an interval containing c and f prime of c does not equal 0, then f inverse is differentiable at f of c. So to take the derivative of an inverse function, let f be a function that is differentiable on an interval I if f has an inverse function g and g is differentiable at any x for which f prime of g of x does not equal 0. So then the g prime of x is equal to 1 over f prime of g of x, and f prime of g of x cannot equal to 0, otherwise this would be undefined. So let's try a couple of problems. Okay, so now we found the derivative of the original function, so now we're going to substitute back the g of x, or the inverse function, into the derivative of the original. So you have negative 12x squared, so x would now be cube root of x plus 4 over negative 4, and this is squared. So then you would get negative 1 over negative 12 x plus 4 over negative 4 to the 2/3. And this would be your final answer. Okay. And then for this one, first find your derivative of the original. So d dx of x to the 7th plus x minus 3. That's equal to 7x to the 6th plus 1. Then find the inverse, which is, so interchange x and y. So x is equal to y to the 7th plus y minus 3. This is the inverse, and as you may notice, it's not easy it'd be complicated to move the y's and the x's all to one side. So now you can just use implicit differentiation. So dy over dx over dy. Yes, dx over dy. So you would get, no. Wait. d over dy. So you would get 1 is equal to 7y to the 6th plus 1 after taking the derivative of that. And then if you remember, the slope of the original is equal to the reciprocal the slopes are reciprocals of each other for inverse and normal functions. So then that means 1 over dx over dy is equal to 1 over 7y the sixth plus 1. And this is the derivative of the inverse function.